Here we are once again solving a very, very difficult physics problem. Just kidding. This one actually isn't that bad. A 12-kilogram box is sliding on a frictionless surface at a speed of 15 meters per second. Frictionless means no impeding force. No impeding force you should think of as meaning constant velocity, right? Zero acceleration. It hits a rough patch where friction is no longer negligible and over a period of 4 seconds slows down to 7 meters per second. What must have been the coefficient of friction between the box and the rough surface? So the first thing that you should do is draw a free body diagram. We've got a 12-kilogram box, and everything is affected by gravity, Fg, which is equal to mg, in this case 12 times 9.8, 12 times 10 is 120, minus 12 times 0.2. Yeah, I'll just use a calculator. I'm getting soft. 12 times 9.8 is 117.6. Okay, and because the box is not falling through the floor and is not getting launched off the floor, we know that the normal force, which opposes the force of gravity, must be the exact same magnitude. So the normal force here is 117.6 newtons as well. Not because we calculated it, but because it must be the same as the gravitational force to keep the box from flying into the air or falling through the floor. Usually when we think of something moving, we think of that as being to the right. So I'm going to say that the initial velocity of the box is 15 meters per second, and the final velocity of the box is 7 meters per second. These aren't always included in a free body diagram, but I want to see which way the friction has to point. Because the velocity used to be to the right, and now it's less to the right, that means that in this free body diagram, we should send the friction to the left. So the force of friction will go to the left. But we know something about the force of friction. It is equal to mu, the coefficient of friction, times the normal force. This is going to be very, very important in a minute. Now we're going to, now that we have all the forces on this diagram, we're going to go and apply Newton's second law. Newton's second law tells us that the net force acting on something is going to be equal to the mass times the acceleration. In particular, we're wondering about the horizontal version of this. So although you may write it without the x's, just to be super clear, I'm going to talk about the horizontal forces and the horizontal acceleration. There is only one horizontal force in this case, and it is friction. This is the only horizontal force. So when I tally the horizontal forces with the intention of filling in the left side of the equation here, I'm only going to get force of friction equals mass times acceleration. And I can do even better than that because I have an expression for that. It's mu times Fn. And at mu times Fn, I also have something better than that. That's mu times 117.6. Oh, look, it's getting pretty specific, right? And then this is going to be equal to the known mass times the currently unknown acceleration. Usually, when you go to calculate a problem using Newton's second law, at some point or another, you're going to have to stop and go grab some info from kinematics. So this right here is not known right now, but you can figure it out. It's not even that bad. So get AX with kinematics. And here's how we're going to do that. You should at this point know that the acceleration, if it's constant acceleration, it will be equal to the change in velocity over the change in time. The change in velocity here is 7 minus 15 remember you do final minus initial, right? Over a period of 4 seconds. 7 minus 15 is -8 divided by 4, and that will be -2 meters per second squared. I did pick this out so that the numbers would work out kind of nicely. So you're welcome. Now I can say this acceleration is going to go in right here. And the equation just lights up like a Christmas tree. I've got mu times 117.6 equals 12 times the acceleration, which is no longer unknown. And looky, I'm going to do multiplication and I'm going to do division. And all of a sudden, the coefficient of friction is isolated. So I'll use handy dandy Mr. Brain here. 12 times 2, make that negative, and then divide by 117.6. And now I'm wondering, why did that end up with a minus sign? Oh, well, it's because I really should have made this negative from the start, because after all, it is pointing to the left. And I've agreed that pointing to the right is positive, pointing to the left is negative. So this should have been negative the whole time, meaning that when I divide out, it will end up being positive. Sorry about that, hiccups happen. So this is going to be 0.20. That's the coefficient of friction. Stop and think for a second. Is this static friction or is it kinetic friction? You should be able to see that it's kinetic friction because it involves actual motion. Static friction is when something is stuck in place and you're trying to get it starting moving. But this is kinetic friction because the box is already moving. And we've solved for it.